Here's another fairly straightforward problem. So we gotta prove that this collection of permutations forms a subgroup. We already know that the monoid the monoid of transformations, well, it's a monoid, and so the multiplication is associative and it's all nice and stuff. And we know that the permutations form a group, and so permutations always have inverses. And so, in order to prove that this is a subgroup, like they say, or like Jacobson says, all we need to prove is that it has closure, meaning that it contains 1, that it's closed under multiplication, and closed under taking inverses. So, more explicitly, since 1 is in, let's subgroup G. So since 1 is contained in G, we must check that for all alpha and beta in G, both alpha beta is in G and alpha inverse is in G. Equivalently, we could have said beta inverse, but doesn't matter. Whatever. You can always flip alpha and beta, so they don't matter. So, let's see here. If alpha or beta is 1, then clearly alpha beta is in G. If alpha equals 1, alpha inverse equals 1 is in G, and likewise for, no, because alpha is the only one we want inverses for. So now we want to actually refer to these permutations. So let A equal, using our notation that is not the one that Jacobson uses. 1, 2, 3, so 1 goes to 2, 2 goes to 3, 3 swings back around, goes to 1. And then, and what's this other one? B is just 1 goes to 3, and 3 goes to 2, and 2 goes to 1. So then AB equals, let's see here, where does it send 1? B sends 1 to 3, and A sends 3 to 1, so AB sends 1 to 1. B sends 2 to 1, A sends 1 to 2, so it sends 2 to 2. B sends 3 to 2, and A sends 2 to 3, so it sends 3 to 3, so AB is just 1. And by a similar argument, you can prove that BA is. So AB and BA are in G, and A inverse equals B is in G. Well, okay, let's just be super pedantic. A inverse equals B is in G, and B inverse equals A is in G. Just in case you are, so this, once we know that A, B, and B, A are both in G, then we know that for every combination of alpha and beta, alpha beta is in G, because this takes care of the scenario of one of them being 1, or the scenario of both of them being not 1. Oh, but wait a minute. We also need to check if they're the same thing, but I'll go and do that. As for inverses, we know inverse of 1 is 1, inverse of A is B, inverse of B is A, and so that's all. So inverses are done. So we're done with inverses. So now we got to check A squared and B squared. A squared equals, let's see here, A sends, let's see here, 1 goes to 2, which goes to 3, so it goes from 1 to 3, 3 goes to 1 goes to 2, so A squared equals 1, 3, 2, which equals B, and it turns out that b squared equals a, because you just do the same thing and it works. So hence, G is a subgroup of S3. And there you go.